Hello, it's Keith here, and this is the third and final of my 6309 assembly programming tutorials. We're looking at more of the weird and wonderful 6309. Now, the first thing I have to say is if you like their tutorials and you want to support them, you can consider buying my book. My second book covers ARM Thumb 658166809 PDP-11 and Risc-V. So if you're into your weird processors, the 6809 is covered there, although obviously 6309 is not. Now we're going to cover the final commands today, a few more mathematics commands basically, and we're going to come across some problems because we started to tread into the territory where the assembler and maybe even the emulator weren't correctly simulating the 6309 functionality, but it's such a rare system, what can you do? Anyway, let's go over and let's check out what we got. Okay, so here is the third and final file we're going to be running today, and let's start off with some pushing and pulling commands. Okay, let's fire up our emulator and let's see what we've done. Now, we of course have our push and pull commands in the past, and we've got the push and pull commands that we've used in the past that will work with the S stack or the U stack. Now, the problem is that those commands basically used a single byte parameter for the combinations of registers that we wanted to push or pull from the stack at that time, and the problem is of course all those bits were used, and so adding the new E, F and W register that is made up of that combination to those commands was not possible. So what's actually happened is we actually have some new commands. We have a push W command, PSHSW, and a PULSW to push and pull W onto the S stack, and we have an alternative PSHUW and PULUW for the user stack. And so these will push the combination of E and F in their 16-bit form W onto or off either of those stacks. And this allows us to back up and restore the W value and effectively the two 8-bit parts. And that's the only way that we can get those onto and off the stack. As I say, the usual commands will not work. So here we've loaded a 32-bit value into Q here, 1, 2, 3, 4, 5, 6, 7, 8. You can see it here. We've pushed that 16-bit W onto the S stack here, and then loaded a new value into Q here, and then we've pulled it back off the stack into W. And you can see here, 1, 2, 3, 4, 5, 6, 7, 8. Reset to auto Fs there, and then W has been restored to 5, 6, 7, 8 there because of that pull command. But obviously D has not been done. Nothing's been done there, and we can't work with D or any other registers with these commands. They only work with with the W registers here. And we've done the same here with the user stack here. You can see 1, 2, 3, 4, 5, 6, 7, 8. And we've restored the 5, 6, 7, 8 part here with this pull here. So if we want to work with the new W register or the EF parts that make it up, those are the commands we will want to use. Now, what we're going to look at next is some quite interesting commands, and some commands I like to see coming from the Z80 world, where we have LDIR, which is a very nice copy command for memory copying. We now have this on the 6809. We now have some transfer M commands. Now these I guess could be transfer multiple or transfer memory, I'm not quite sure, but basically these allow us to do sequential commands. So what we've got here is a sequence of unused memory bytes here before we've done anything here at memory address 7100. And what we have here is some test data, a sequence of bytes here. And what we're going to do is we're going to use this transfer M command, transfer multiple. And what this does is it takes a memory address in X and a memory address in Y and a number of bytes in W. And so what we're going to do here is we're going to set X to test data plus 4, Y to 7104, and W to 4 bytes effectively. And what we're saying here is transfer from X to Y, incrementing X and Y after each transfer. And we're going to transfer 4 bytes in total. And you can see here that because X was test data plus 4, so basically the second line here, 89 A, B, C, D, E, F, and because our destination was 7104, we have transferred 4 bytes, 89 A, B, C, D, E, F, to this second half here. So that is what this command has done. Now, in that case, we're incrementing X and Y after each transfer. We can decrement them as well. So here they're going down. Now we've started from the same byte address. So basically 89 will have been overwritten here, and then we've gone down, effectively leaving 7100 unused because we only transferred 4 bytes here with our decrement because W was set to 4 there. Now those are fairly logical copy commands, so copying that way or copying that way. We have some slightly more unusual commands though, and I think the next one, what we're doing here is we're basically transferring from a sequence of source addresses to a single destination address. Now why would you want to do that, you might think? Well, I would guess that this would be quite handy if you were needing to transfer to a memory mapped register. For example, if you've got a VRAM port and you've got a data port and you want to transfer a sprite from your RAM to the VRAM, you might want to transfer all the bytes from RAM to a single port that is the data port of your video hardware. And I think this would be quite handy for that. So what we've done here is we've transferred from test data plus 4 to port address 7104, which is a single address. And so basically we're going to transfer consecutively 8, 9, A, B, C, D, E and F all to the same memory address here, and so you can only see the final one, EF, here because they've all been transferred to memory address 7104 here. As I say, more useful for memory mapped hardware, I think. Now what might be more useful is the opposite. What we can do is we can transfer a single source address to a sequence of destination addresses here. So we're incrementing Y after each write, but we're leaving X the same, and so this is effectively going to copy the address test data plus 4 to a sequence of 4 bytes from 7104 onwards, and you can see that is what has happened here, 89898989. So it could be quite handy if you want to fill a range with zeros or with some other byte. You can do that with this command. Quite handy. Now it should be noted though that there's no version to go down in memory, so we can only go up in memory here. So you will need to make sure your memory ranges are correctly defined. Probably not very necessary though. There are times you need to go backwards in memory if you're doing a scrolling effect, for example. Depending whether you go that way or whether you go that way, you will potentially be overwriting the wrong data if you use the wrong transfer command if you're doing a scrolling effect, but not so necessary if you're filling an entire range with a single byte. So you just need to make sure your ranges are set correctly with that command. Okay, now that's transfers. What we're going to look at next is the new multiply and divide commands. So this is one of the times when we actually have a command that works in 32 bits. So what have we got? Well, we've got mul-d. Now this will take a value in the D register, which is a 16-bit register of course, and it will multiply it by the value and it will store the result in the 32-bit queue. So what we've done here is we've loaded D with 0FED and we've multiplied it by hexadecimal 100. Well, you can see here 0FED here, and we've effectively multiplied that, and you can see that that is now in the 32-bit combination of D and W together. So that has been multiplied by hexadecimal 100 there. And so you can see our 32-bit value is now 000FED00 there. So that multiplication has there worked. We also have a divide queue, which is kind of the opposite, I guess. So what this will effectively do is it will take the value in Q, which we've given this 0110023 here, and it will divide it by the immediate here. And the result is that W is the whole number value and D is the remainder. So we've got our 01123 here, and we've divided that and by the hexadecimal 100, and W is now 1100, which is the whole number part, and 23 is the remainder, which is the bytes that were pushed out of W, out of Q rather, by that division there. So that is how we can get our remainder. Now our final command that we would want to look at is div-d. Now div-d is effectively kind of the opposite of the original multiply command from the 6809. Now unfortunately there's a problem, it doesn't actually assemble correctly. When I assembled this it didn't work, and the reason it seems to not work is the immediate parameter here should be being compiled as a single byte. So this should compile to 118D10. However, the assembler I'm using was compiling it to 118D0010 as if it was a 16-bit number, which, according to the documentation I've seen and according to the result of the emulator, is not correct. So I've basically specified my div-d command as bytecode here. So that is the equivalent of the command div-d with an immediate of hexadecimal 10 there. And if we do this with our value of 0203 in D here, this will set the B part to the whole number part and the A part to the remainder. And so the whole number part is 20 and the remainder is 3. And so the div d command does work, but it doesn't seem to assemble correctly with this assembler, which, as I say, is understandable when you consider, the fact that this is, this is an instruction set in a CPU that was never really used. Now, the final commands we're going to very, very quickly discuss is these new commands. We've got a sequence of commands that work with a single bit of a source register and a single bit of a memory address. Now, these there's a wide variety of them. There's load bit, there's store bit, there's bit and, bit or, bit or, bit test, and a few other ones as well. Now, basically, these work with a rather strange format. There is the command, then there is the register, followed by a dot, followed by the bit number of the register, and then an address, and followed by a dot, and followed by a bit that we want to change of the address. So basically, the two bits don't need to match. So we can do a bit of the condition code register with a different bit of the destination and memory address in the 0 page here. The problem is these do not work correctly. As far as I can tell, I think the assembler is assembling them correctly, but I think the emulator is actually, I think the processor emulator is not emulating them correctly, which sounds ridiculous, I know, but it seems to be that some of the registers are swapped around. Like when you try and do it on A, it actually does it on B and things. And when you do it on the condition code, it seems to do it on B. So we're not actually going to discuss these or show the result, because, as I say, I don't think they're actually producing the results that the code should be producing. So it's just going to get far too confusing, and you can't use them reliably anyway, as far as I can tell. So some fascinating commands in the 6309 instruction set. I am always very interesting to see commands with new syntaxes introduced in these processors, but as I say, they're quite complex at the best of times, and as far as I can tell, the emulator unfortunately isn't running them correctly, which, as I say, I totally understand considering this is so obscure. Anyway, you can go to my website, you can download the build scripts and the examples, and you can have a go with yourself, and maybe one day you will find an assembler and an emulator that work with those commands correctly, and you can have a play with them. Anyway, I hope you've enjoyed what you've seen today. As I say, if you want to support my content, please consider buying my book, and really helps me out. It helps justify keeping making such weird tutorials. Thanks for watching today anyway, and goodbye.